So this is a stoichiometry problem. The only difference is we're dealing with a gas. And so normally what we do is we go, let's say, grams of zinc. So we go grams of zinc to moles of zinc, and the moles of zinc to moles of hydrogen, and the moles of hydrogen to grams of hydrogen. But in this case, they don't want us to tell me how many grams of hydrogen formed. They want me to tell them how many liters of hydrogen gas formed. And the number of liters is going to depend on how many grams. The more grams of hydrogen, the bigger the volume. So it's going to depend on the amount. In other words, the amount can be given in grams, the amount can be given in moles. So the more moles of hydrogen, the bigger the volume. And so the volume is going to depend on the moles, but it also depends on the pressure and the temperature. High pressure means smaller volume, low pressure means bigger volume. And it also depends on temperature. Low temperature, gases contract. So at low temperature, we have a smaller volume. At high temperatures, gases expand. And so the volume of hydrogen depends, what pressure are we generating it and what temperature. And so they tell us the temperature and the pressure. Standard temperature is 0 degrees C, 273 Kelvin, and standard pressure is 1 atmosphere or 1 bar, depending on the U.S. U.S. is 1 atmosphere, Canada would be 1 bar. So we'll use 1 atmosphere. And so what we're going to do is we're going to do this. We're going to go from grams of zinc to moles of zinc, and then moles of zinc to moles of hydrogen. Once we're at moles of hydrogen, we have 2 options there that we can do. And, let me talk. Grams of zinc to moles of zinc, moles of zinc to moles of hydrogen. Now, moles of hydrogen, we have one choice, and that is we can just calculate the volume using the ideal gas law. The volume is going to equal nRT over P, where we're going to take this moles of hydrogen and plug it in. So moles of hydrogen here, it's just going to be plugged in here, there. And then STP, we know the temperature and the pressure because they tell us STP here. So I'll tell you what I memorized. What I memorized was the molar volume of the gas at STP, which I'm not going to have you necessarily do. And so the other option is we just convert it straight to volume of hydrogen using the molar volume of hydrogen at STP. And so this requires a calculation here. This is either memorized or, actually I didn't ask you to memorize this one, STP. What did I ask you to memorize? Actually, you don't have to memorize that. That's R, the gas constant. Yeah, the one I asked you, the molar volume I asked you to memorize was the molar volume at RT in 1 atmosphere, which was
298 Kelvin over 25.
Yeah, which is going to be
24.5.
Yeah, 24.5. All right, so we have 2 choices. We could stop here, calculate the moles of hydrogen and plug it in here, or we can calculate one more conversion factor. The molar volume is A, it's memorized. So a lot of people have this memorized, and I did, Or B, it's calculated. I don't recommend memorizing this one. And so let's go ahead and calculate it. Now, the molar volume equation can be memorized or it can be derived. The molar volume equation is just RT over P. We could derive it too. I derived it last time. And so let's go ahead with R. R is 0.08206 liters atmosphere per mole Kelvin. It's important that you put the units in here because it'll tell you if you got the equation correct or if you got the equation wrong. Because we know the molar volume should be liters per mole divided by the pressure. The pressure is going to be 1 atm exactly. And so let's look at the units here. The atms cancel, the kelvins cancel, and that gives us liters per mole. And so I know that this equation's correct. Sometimes I don't remember the equation. Sometimes I'll get a P over RT, but if you get a P over RT, then it comes out moles per liter. Okay. But we know what the units are. So what does this come out to? So just punch it out in your calculator. I'll do that here. 0.08206 times 273 equals 22.40 liters per mole. This is the number I've memorized for many, many, many years. Let's see. Let me just see something really quick. The 22.4 liters per mole, 22.4 liters per mole, 22.4 liters per mole. Lots of people had to memorize it, not just me. Even on, let's see. What is the molar volume of gas at STP? 22.4. So we could just tack that on as a conversion factor. You know, what we can do is we can just go from moles of hydrogen straight to liters of hydrogen gas using the molar volume as a conversion factor. And so let's see what they did in solving this particular problem. They used the molar volume method here. And they go from grams of zinc to moles of zinc using the molar mass converted. And then moles of zinc to moles of hydrogen using the mole ratio, 1-to-1 mole ratio. The moles of hydrogen to liters of hydrogen. But look at it, didn't I just say 22.4? They got 22.7. What's the difference? Standard pressure. They must be measuring pressure as 1 bar instead of 1 atmosphere. And so their STP is using bars. A bar is a little bit smaller, therefore, if it's a little bit smaller pressure, then the gas can expand a little bit more. Does that make sense? But if we use atmospheres, we're going to get a slightly different number. And so if we use atmosphere, 1 atmosphere is standard pressure, this would be 22.4 rather than 22.7. Is that clear? But do we really work at 0 degrees C? No. In fact, really we work at room temperature. And so what I want to do is I just want to redo this problem, but not at STP. I want to redo this problem at 1 atmosphere and room temperature. And so we see what's going to happen here. If we do it, okay. Let's go ahead and do it here. If we do it 1 atmosphere instead of 1 bar, well, how many liters do we get? And so I'm going to go ahead and calculate that. We would get 14.6 liters. So if we did it at STP with 1 atmosphere as being standard pressure, the volume of hydrogen comes out a little bit less. It's 14.6 0.0 liters of hydrogen. That's because 1 atmosphere is slightly higher pressure, so it's going to compress it a little bit more. It's actually the same amount of hydrogen, you know, in terms of moles or grams. We're generating the exact same amount. It's just compressing it more, compressing the volume more, or expanding the volume, depending on what the external pressure is. And so let's redo this problem, but what we're going to do is we're going to do it at room temperature. Okay. And 1 atmosphere. And so at RT and 1 atmosphere, how much hydrogen am I going to generate? And so I still have a choice. I can either do the ideal gas, or I can do the molar volume of hydrogen. And so we'll do the molar volume one first. If we do the molar volume of hydrogen, I could have it memorized. If I have it memorized, what is the molar volume of a gas? Any gas. This is a molar volume of any gas at room temperature in 1 atmosphere. 1 mole of any gas at room temperature in 1 atmosphere occupies how many liters? Somebody just had it. Rolando, was that you?
Yeah, 24.5.
24.5 liters per mole. So this is the molar volume at RT and 1 atmosphere. So I might have it memorized. If I don't have it memorized, I could calculate it. The molar volume is equal to RT over P. Then just calculate. It would come out to 24.5, but since it's kind of useful, since we do most reactions we do are going to be at room temperature and 1 atmosphere, this turns out to be a useful number to know. And so how much hydrogen would we generate under these conditions? You know, well, we're going to generate the exact same amount in terms of moles and grams. It's just a little bigger or smaller depending on how much we compress it. And so we'll do the calculation here. 42.7 grams of zinc times 1 mole of zinc weighs 65.38 grams of zinc. Grams of zinc cancel. And then I'll just do a mole to mole. 1 mole of hydrogen for every 1 mole of zinc. Mole to mole conversion. And then here I have 2 choices. One, I could stop here and go on the above branch. So if I stop here, how many moles does that come out to? Let's see. So I go 42.7 divided by 65.38 times 1 divided by 1 equals 0.6531 moles. So this comes out to 0.6531 moles of hydrogen. So I'm going on the top branch here. So if I know the moles of hydrogen, then I could figure out the volume of hydrogen. The volume of hydrogen is equal to the moles of hydrogen times R times the temperature of the hydrogen divided by P. And so the moles of hydrogen, it would be 0.6531 moles times R. Times R, which would be 0.08206 liters times atmosphere divided by mole Kelvin, times T, which would be 298 Kelvin, divided by P, which I'm calling exactly 1 atmosphere here. So let's go ahead and calculate so times 0.08206 times 298. 15.97 liters of hydrogen. Okay, the other option is this. If I just go down, I'm just going to multiply it by the next conversion factor. The next conversion factor is 24.5 liters of gas per mole of gas, any gas. So this conversion factor is valid not just for hydrogen, but whatever gas we're looking at RT and 1 atmosphere. And so let's redo the calculation using the bottom branch. So the advantage of the bottom branch is we're just using a regular dimensional analysis rather than stopping here and then doing an algebraic calculation there. And so I'm going to get 42.7 divided by 6538 times 24.5. And I get 16.00 liters of hydrogen. So anyway, when I round this to the correct number of bigs, I'm going to get 16.0 liters of hydrogen. The same here, 16.0 liters of hydrogen. Difference would be attributable to round off there. We rounded to 24.5. It was actually 24.47, something like that. Recall that? And I didn't actually round that. Anyway, we get the same answer. So either way, you could do it. But anyway, so when we go to a higher temperature, it's going to occupy more space. And so we calculate 14.6 liters at 0 degrees C, but at 298 Kelvin, the volume increases to 16 liters of hydrogen. Time are we at? Ooh, we're over time. Okay, let me stop here.